Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Today we're going to continue our discussion on functions, and we are going to specifically look at linear functions, which you'll come to find out are very similar to the linear equations we worked with all during our last unit. So let's just jump right in. I guess you could call it a game or an activity. There's a flow chart to the right here. And you are going to follow those steps and perform those steps for 4 integers. So again, if you don't remember what integers are, they start at 0 and they go in both directions, positive and negative whole numbers. So pick 4 of these, perform those operations on all 4, and write down your results. Then for number 2, you're going to make a prediction about how you could figure out the final number given any starting number without going through all of the steps. So would you have to go through all 3 of those steps, or is there a way for you to shorten the process? Then, for part 3, you don't have a partner, so you're just going to see if you could find an integer for which your process doesn't work. And if you do, write down what that integer was and why. Finally, you're going to see if you can write an equation to represent this process, where x is your initial number and y is the final number. So x would be what you started off with, and then y would be what you ended up with. And you would see if you could come up with the different operations required to relate the x and the y correctly together. So this may take you a few minutes. Pause the video. When you feel like you've answered all 4, or you feel like you're not really sure where to go next after thinking about it, feel free to join us back here for a discussion. All right, so I'm going to write out one example, and then just to make sure that you did it the way you're supposed to, and then we're just going to put the first number and the ending number up there. I'm going to start with -4. Oops, let's get a pen out. So we've got -4. I need to multiply that number by 9. So that's step number 1. So I multiply that number by 9, I get -36. Step number 2 says subtract your original number. Sorry, that should be -36. So I get -36 minus -4. So that's going to give me -36 plus 4, which gives me -32. On to step number 3. I divide that number by 4. So I've got -32 divided by 4, and that gives me -8. So my initial number was -4. My ending number was -8. I will keep that up here. So I start with -4. I end with -8. If I chose 0, well, multiply 0 by 9, I get 0. Subtract 0, I get 0. And if I divide 0 by 4, I get 0. Let's do 1. Multiply 1 by 9, I get 9. Subtract 1 from 9, I get 8. Divide 8 by 4, I get 2. And I'll do one more. Let's do a big one. Let's do 26. Multiply 26 by 9, that gives me 234. Subtract 26 from 234, that gives me 208. If I divide 208 by 4, that gives me 52. So those are the 4 integers I chose. You can see the relationship between the starting and the ending integer there. And number 2 says, make a prediction about how you could figure out the final number giving any starting number without going through all those steps. So is there just one step I could perform on these initial integers that would get me the final one? And maybe you saw this relationship from your examples, but I could just multiply initial number by 2. And there are, of course, some creative ways you could write that, right? You could say divide by 1/2, or you could come up with something else. But This is the most straightforward path, just multiplying the initial number by 2, right? -4 times 2 is -8. 0 times 2 is still 0. 1 times 2 is 2. 26 times 2 is 52. So you could think about, okay, is there an integer that doesn't work for this method? But I've covered all the different types of integers, right? I've covered the negative ones with -4. I covered 0. And I covered the positive ones. We can't use fractions or decimals because those aren't integers. So it is likely that this works for every integer. Now, the last part was, could we write an equation where x was the initial number and y was the ending number? Well, if we start with our initial number, and again, this is going to be number 4. I'm just not going to scroll down because I don't want to lose everything. So if I start with my initial number, we said we have to multiply that by 2 to get my ending number. So this would be an equation 2x equals y, where x is the initial number, y is the ending number. And believe it or not, this is a function. It looks, again, we've worked with equations like 2x equals y before, but this would be considered a function as well. So let's move on. Let's talk a little bit more about these things called functions. So just like we said, we have linear equations that we discussed last unit, where we have y equals something. That linear equation, we could think about what form that's in. Hopefully we could identify that as being slope-intercept form. And then we also have something called function notation. So you'll notice that those two things, those two equations, the only difference is that they replace the y with f of x. Well, that's just function notation. We read that f of x. So you should be familiar with the left-hand column, as we've worked with linear equations quite a bit before. That's fixed on yours, but it's not fixed on mine yet. Quite a bit before. In this unit, we'll start to understand linear functions, which, as you may have guessed from above, are similar to linear equations. So basically, the biggest difference between a linear equation and a linear function is that a function may have an f of x, or we'll see down below, we can change this to a bunch of different things, right? This just tells us what we're calling the function. When we have f of x, our function is function f. But I could put g of x if I wanted to call the function g. Or I could put h of x, or a variety of other different letters. So don't let that f of x fool you or confuse you. It basically means the same thing as a y, right? It's just different notation. All right, so it says right here for function, a function is a rule that takes an input, remember inputs are part of our domain, and produces an output. And we know that outputs make up our range. The function always performs the same operations on the input regardless of what the input is. So right, just as we looked at above, it didn't matter what integer I chose to start with. I was still going to perform the same operation on it as I did any of the other ones. And then just what I was discussing above, function notation. This is a method for writing variables as a function of other variables. So when using function notation, we can replace the y in our equation with f of x. Again, that's read a function of x, or f of x for short. Linear functions are functions that have a constant slope. This will be a line, or part of a line when you graph it. So again, Unit 5, we spent graphing lines. Linear functions are also going to be lines as well. Let's talk about an important concept, evaluating functions. So for functions, we start with inputs. We do some operations to them, and we are left with outputs. Right? Again, think about our example at the very beginning of this lesson. We chose a number. That would be an input. We performed several different operations on that number. We then were left with an output. So this is just a little diagram. It's called a function machine, but it's just showing you the idea of an input is a number that we input or substitute into the function. The function then performs different operations on that input, and it spits out or it gives us an output. So our x's are the inputs. These x's are our inputs, and the f of x's are our outputs. So let's go through a little example of what we're talking about here. Let's say I start with the input, -1. So I'm going to take this -1, I'm going to stick it right into my function machine. Well, this function is telling me that any input, and this is what we're going to do, we start off with the original function, f of x is equal to 7x minus 3. But when we choose an x value, this becomes f of -1, because we're choosing -1 as our x value, as our input. Well, that means we're going to substitute -1 in for the x in our function. So the first thing we're going to do, and again, we would just follow order of operations, we are going to multiply the -1 by 7 to get -7. Then we're going to combine our like terms, -7 minus 3. And that's going to give us -10. So if we stick or input -1 into our function, what pops out is a -10. Right? So it travels through here, and again, it's just a visual way of describing what's going on. Really, it's just mathematical operations that are occurring. But after we have applied all the function rules, we are left with -10, and that is our f of x value. In this case, it would be our f of -1 value. So we can do that with any number that we're allowed to substitute into the function. Here, we are going to try it with 0, 2, and 5. Let's do one more together, and then you can try the other two on your own. If I'm going to do x is equal to 0, well, again, I start off with my original function. And if I'm choosing 0 for my x value, I replace all of my x's with 0. Then I just begin to simplify. 7 times 0 is 0. And 0 minus 3 is -3. So -3 becomes my output when my input is 0. We do have to understand this other concept right here. Right? This is, notice how I've been saying f of x. I haven't been saying f times x. Right? This does not mean multiplication on the left-hand side. This does not mean f times 0 down here for these other three. Right? This is read f of 0. What this means is that I've substituted in 0 for my x, and I'm performing operations on the other side of my equal sign to figure out what my output is. But this right here stays the same. Remember, this is like our y value. Right? I could replace this f of x here and just write y instead. Right? We've worked with x and y tables before. Right? We're just now replacing the y's with f of x's because we're working with functions rather than linear equations. But they're almost exactly the same thing. Right? The notation is just what's different. For linear equations, we're talking about y's and x's. For functions, we have x's, but we also have this new thing, f of x, that replaces our y. So go ahead, attempt this process for inputs 2 and 5 and see what your outputs are. All right, so if you substitute in 2 into your function, you should get 11. And if you substitute in 5, you should get 32. So again, this is just called evaluating a function for a specific input. If they give us a number to input into a function, we perform all the required operations and we are left with an output. Let's see what's on the next page. We can also use other letters than just F to name our functions, and I referenced this above, right? We could use G, we could use H, we could use M, we could use Q, we could use any letter of the alphabet. The one thing you won't see is having the same letter for your input as you do your output, right? So what we won't see is x of x is equal to 2x minus 3. You could choose any other letter for this x because we don't want it to be the same as our input. But other than that, again, as long as those input and outputs aren't the same, you will be okay. I'm not going to go through this top example because we just did an example like that on the last page, but you could go ahead and perform all the operations for the given inputs and see what your outputs are. Again, in this case, our t's are the inputs, and our g of t's would be the outputs. Let's move on to 3 and 4. So no more function machines. I think we have the idea of what we need to do when we are trying to evaluate a function. But let's look at number 5. So again, there's no machine diagram here. We just are left with our function. And we are being asked to evaluate this function when x is equal to 4. So pause the video, take 60 seconds, think about what we did up above, and see if you could apply it here, even though there's no diagram. Okay, so again, all I'm doing is when x is equal to 4, that means I replace all the x's with 4s. So anywhere I see an x, I replace it with a 4. Remember, over here, this is not h times 4. This is read h of 4. So that's going to stay the same. This represents my output when my input is 4. Order of operations, I got to do my exponents first. So I get 4 squared is equal to 16. I then can multiply, so 3 times 16 is 48. We'll come up here. 48 minus 10 is equal to 38. So h of 4 is equal to 38. That means when my input is 4, my output is equal to 38. You can go ahead and try numbers 3, 4, and 6. We will do those in class, but if you want to get a head start, you can. Same idea, just different functions. So the rules are going to be different. The operations are going to be different. Different type of example here on our last page. Now we're going to go the other way. So it says sometimes we may be given the value of the function and need to find the x value that gives us that output. So it's essentially like we're working backwards. If I went back up here to our function machine, it would be like understanding what my output was. Let's say my output was 18. You would need to then figure out, well, what number did I input to get 18? So that's what we're trying to figure out in the last page. We're doing the reverse process. So it says, given the function f of x is equal to negative 3 plus 14, find the x value that makes f of x equal to 53. Okay, so we know what our output is. We know our output is equal to 53. So what we can do, I know that these two things are equal. So I can substitute in 53 for f of x, because I know 53 is equal to f of x. So I get 53 is equal to negative 3x plus 14. This is the key here, right? I think we could understand how to solve for x moving forward, but we have to understand that what the substitution occurring is and why we're doing it, right? They're telling us that an output is 53. Well, f of x, right, this represents our outputs. So we're substituting in our specific output, 53, in for f of x and trying to figure out what the input is. Our input being our x value. So let's go ahead and solve. I'm going to subtract 14 from both sides. So I'm going to get 39 is equal to negative 3x. If I divide both sides by negative 3, I'm going to get negative 13 is equal to x. So the input that gives me an output of 53 is negative 13. And you could double check to make sure that this is true. Let's start with negative 13. So if I start with my original function, and I have an input of negative 13, so f of negative 13, remember I'm going to replace every x with negative 13. Now I would just simplify. F of negative 13 is equal to negative 3 times negative 13 is going to give me positive 39. And then f of negative 13 is equal to 53. So that checks out, right? When I substitute in negative 13 for my input, I get 53 as an output. So my process working backward was correct. Okay, that's where we're going to wrap up this video. There are some other problems below that work the same way. We're finding inputs rather than outputs here. So hopefully you can use the example at the top to help you with those. All right, have a great rest of your day, and I will look forward to seeing you next time.